This presentation is a joint venture with my dear colleague, Dr. Gerhard Nötzl-Steidle. And we're starting in this talk with an idea of the virtual product development process, as everybody of you will know. Then I want to show you which is the new simulation workflow, including PERMAS. And of course, for a typical simulation workflow, we always need some proof of concept. So I want to give you also some details on this workflow and the tools therein. Finally, I'm closing my talk with a conclusion. So starting with the virtual product development, of course, first of all, there has to be a product idea, which you can see on the upper bound here. Then a virtual design is created, an analysis model is developed before we can start on the bottom with a simulation and also a result evaluation. Afterwards, there can be a loop of that and before it finalized in a real product. And for the real product, of course, there have to be a lot of specification, starting from the CAD geometry of manufacturing constraints and prototype testing. Also, the quality assurance is a big point. In the virtual design, on the right-hand side, you can see that for the virtual twin, we have to do some critical points in the CAD to FE meshing. We have, of course, the physics included in the model, with a huge part, including boundary, loading condition, and also some other limitations. So let me summarize these steps for the FEA simulation workflow into 4 parts: the CAD FE meshing, the completion for the FEA model by physical integrations, then on the right lower side, of course, simulation with the finite elements, and finally, the result review. For these 4 parts, we want to use specific tools which can integrate very smoothly in your process. And for this workflow toolchain, including PERMAS as the solver, I want to present you the tool for the meshing, which is in cooperation with a DEP, which is called MeshWorks. Then on the green part, we're using for the physical definitions our VisPER pre-processing tool. Then going to PERMAS, of course, and for the post-processing tool, we also using VisPER. The complete process of different tools can be controlled by a workflow toolchain manager. And here I want to present you the PERMAS control center to applicate all the tools. Between each tool, there is an interface. As you know, from meshing to physical modding or from another solver to PERMAS, you always have an interface. And this is a crucial point for the speed of your workflow. So if you have a very good and smooth interface, then all is fine. And the best interface, of course, is no interface. So I present you in the following steps also the total workflow, but we look into some details of different tools. For the proof of concept, I want to apply the complete tool chain, which is shown here, on a transmission housing. Just a demonstration model. We included here some gasket layers as sealing parts, and of course we had a lot of screws here in this model of different sizes. So we have to manage all the tools, build up the FEA model, perform the analysis, which is an easy task in this case, and to review the results. What I want to do is here to point out the tool transitions, as I mentioned, and validate the workflow efficiency of this tool chain. For more details on that, I would invite you to visit our info point over there, where we have the model on screen. So starting by the mentioned PERMAS Control Center, we have a visual GUI here with possibility to handle all the files which you are needed in your process, and of course all the tools for these files. On the right-hand side, you can see different tool handling buttons. For example, the mesher, which in this tool workflow chain is MeshWorks. Then we have VisPER button, a PERMAS button, and a lot of more buttons which represent further tools, because every one of you has some own, for example, Python tools, which integrates into your workflow. And here we can add them in this PERMAS control center. Starting with the MeshWorks as a meshing tool, I want to present you a short overview. MeshWorks is developed by Detroit Engineered Products, located in Troy, Michigan, USA. We're starting from the CAD geometry by importing the CAD and perform some meshing tasks here. There are automatic FE meshing functionalities, different modules and assistant tools to verify that you get an optimal mesh quality in this case. So MeshWorks has a huge graphical interface, and perhaps someone of you is familiar with this overview. We have our primary toolbars, the canvas, the model tree on the left side, and some further toolbars. And also a very important point I want to figure out is, for this process, there are automatic surface pairing algorithms inside of MeshWorks. So if you want to get all the connection between two parts of your meshed model, then by the automatic surface pairing, you can detect surfaces and additionally pair the correct surfaces into your contact or MPC definitions. So you can, this can be done automatically in MeshWorks, and as a final product, you get the mesh, you get the surfaces, and some coupling informations. Those, it's the lower point. In this case here, we have 3 surface pairings, which are defined as contacts, and 61 pairings, which will be incompatible mesh coupling definitions by MPCs. Then we go further on the interface to the pre-processing part for the physics. This is very essential, as I mentioned, because it determines the speed of your workflow. In this case, on the left side, we're starting with this mentioned surface pairings, and we developed an interface which combines a PERMAS DAT file. This DAT file includes the basic solid mesh data and other structural things like sets and surfaces, and also, of course, some element property connections. And that's all. Further informations on how to get the surface pairings as contacts or MPCs for PERMAS, this is included in a separate Python file. We call it Python macro file. VisPER is able to read those Python macro files, and then if you read this DAT file and this Python macro file, you automatically get the creation of your contact definitions inside VisPER and your iSurface definitions beside your mesh. So your benefits of the automatic detection of surface pairs inside your meshing tool is transported to the VisPER functionality, and you do not have additional effort. As we can see here, the next steps is to fulfill the physical definitions within VisPER. For example, I want to give you a short overview over the pretension wizards in the new version 20, because in many parts you will find screws. Of course, we remember that we start with only mesh and surfaces, and we have no ideas where screws are located, but because of the mesh definitions. So with this new version, it's possible that you only open the pretension wizard, and here we can see that you have a lot of screws. Finally, you create the detect button, and then after a few seconds, all screw pairings are automatically detected, and you can visualize these definitions and control them easily by clicking through different screws. And here you find the thread coupling definitions. And if it's okay for you, you can accept them, and that's all for the pretension definitions. Here we have 56 pretension threads created. Afterwards, we complete the physical modeling and export all those things as a DAT file. You can handle it by a separate DAT file creation if you want to distinguish mesh data and physical data. This is no problem here in VisPER and PERMAS. And of course, you have the possibility in VisPER to verify your final model by element quality checks or further PERMAS checks. And afterwards, in this presentation now comes the easy task. You just execute PERMAS, for this example, as in contact analysis. Here's a short model overview. We have 13 million unknowns as the outline. And as you can see, this is a typical PERMAS output. And for the result evaluation, we're using the binary HDF file format of PERMAS. So, as you remember, I said something about the interfaces, and now I skipped from VisPER to PERMAS by directly sliding. So I want to mention that here there is no really interface between VisPER and PERMAS because it's setting on top of VisPER. So it's just a graphical user interface, and we live all in the same PERMAS world with the same PERMAS DAT file. And afterwards, from PERMAS to VisPER post-processing, it's the same. We created this HDF file. We can use our model files or even our UCI files to read within VisPER. And here we are by starting our post-processing features. So with a fast HDF reading in VisPER, you're starting with the results and data dialog, which gives you a nice and quick overview which result items are available on your result file. Then you have a categorization of some properties, these result types, even if it's scalar, a vector, a tensor, and so on. For this presentation, I present you one or two examples, like the contact pressure as a scalar value. And it is possible for you that you can switch in VisPER between the post-processing functionality and the pre-processing functionality simultaneously. So if you remember, we used VisPER to create the physical definition, and of course, in this step, if you are missing, for example, some nodal point sets for result evaluation, there's no problem. You do not have to switch some tools or starting some new applications. Just go into VisPER and where you are and create some node sets, and there you are. So you also have the possibility to record all your steps in VisPER within a Python script. So you have the flexible automation possibility, and if you recalculating your things later on, you can execute this Python script, and all the processes like selecting results, selecting nodes, creating some plots, and so on are executed automatically. So I want to focus now on these different results and result viewing possibilities in the new VisPER version. As I said, we're taking a look on this contract results on the oil pan here in this model. And we're starting by getting a viewer, and this image is from the last slide. So clicking this on, at once you have displayed the selected results. You have to not to click anymore. And now it's possible to simultaneously visualize another result type. Here we have a scalar result, but if you want to show some forces, like reaction forces, in the same view, but on another result type, you can do it by just checking on the box of the result item. For this example, we use the reactDs as vector visualization, and thanks to the multi-viewer concept of VisPER, you can see that is one window, so one workspace, and only the small windows, which we call viewers, inside of VisPER are splitted into two things, one which showing the scalar results, one's the vectors. It is even possible to show both results into one viewer, if you like that. But I want to mention out this multi-viewer concept here. Then I want to give you the information that when we look at the reaction forces here, as you can see, this is represented typically in the global coordinate system. But if you are interested in some results in a local system like this of the oil pump, which is rotated a little bit, then you have the possibility in VisPER to transform your results on the fly, which I will show you. So take a look on the lower picture, and you will see a small rotation now. And here we have selected not the complete reaction forces, but only the local set component in the local system. Yeah? So this is represented by VisPER as a transformed result. And further on, now we have the possibility to create a selected plot, XY plot, yeah? Because we want to know where is the lowest value of the force around the circumference path. So we made a nodal point selection or just a path selection by a few clicks. And if we have done this on the left side, you can see a small table where you can configure yourself which XY data you want to plot. Now, I have selected here a path length and also the set force. And if we click then on the plot button, we have an XY plot immediately shown on our selected results. It's all within VisPER integrated. So further on, we have the possibility now with VisPER 20 that you can customize some annotation results. Yeah? If we want to know where is here our minimum on this circumference path, we put on an automatism, just clicking on the result table and say VisPER, show me the minimum and maximum, for example. And here we are applying an annotation, and you can write inside the annotation your text as you want and format it as you need it. Also, it is possible to store your customized templates for later usage. Afterwards, if we have reviewed the results, we are going on. What to do now? Is this product now acceptable? So we're finished and we'll be fine? Or do we have to do further steps? For example, as we heard yesterday, processing another cut continuation loop, so we can go to a cut geometry. Or if we want to use some remeshing information, of course, we can use our basic DAT file from the beginning and going back, for example, to our meshing tool, MeshWorks, yeah, creating new cut geometries or remeshing some parts. Yeah? And if you're using a multiple DAT concept, you can easily adapt a new meshing region, a small one, and you do not have to remodel all the physical definition. You can just use some additional tools inside VisPER, like the add and replace tool. And for a new meshing area, then all surfaces are adapted automatically. And with the adapted surfaces, you automatically create the new contact definitions, for example. So let me come to my conclusion. What do we have seen here? The PERMAS Control Center is a toolchain manager for proposed simulation workflow. Second, that Control Center promotes a configurable toolchain for customizable workflows and process integration by means that you can integrate your own Python scripts if you want, yeah, or you can customize some other tools. We have inside PERMAS synchronized PERMAS interfaces which ensure a high workflow performance. So we take always a look that the interface transition is a smooth one, so that we can integrate the whole process very quickly for your needs. Additional Python scripts support flexible automation in all process steps. So you do not only have the possibility to use your Python scripts for your workflow, but also Python scripts inside of VisPER, for example, to manage those things inside a tool or outside a tool. Multiple file input and output enables efficient data transfer and data storage. This is, as we have heard with the integrated fatigue example, we have an own parallelization mechanism, and we are also engaged to perform high computation simulations with less of memory and less of hard drive storage. Finally, fast data communication due to internally optimized PERMAS database access is integrated in PERMAS. And if you're interested in such a process or want to test all the new features within VisPER and PERMAS, it's possible that you can use all these tools here mentioned in this workflow chain, including MeshWorks, as one license package. For the flexible license unit management, we have integrated all this one as one package we can ship out to a customer for the installation, and you have all the tools available at your home. So finally, I want to thank you for your attention, and I'm regarding or hoping for your questions. Otherwise, please welcome to our demo point for further investigations of this model process. Thank you very much.
No, so thank you very much for your nice presentation, Roland. We ran a bit out of time, so I would just ask all who want to pose questions to Roland to look for him. He will be available afterwards. Thank you very much.
Vielen Dank.